point of view, when one is designing such a network, how can he make sure that he minimizes the losses, taking into account the eventual failures of segments? Is he supposed to do all those calculations for each possible path, or what?
Yes, it's really a very good question, because it allows me to enter into details and to explain the difference which there is between pre-programmed routing and dynamical routing. Pre-programmed routing simply means that we are speaking of networks which have a reduced number of nodes. We are not speaking about huge networks. I've been showing yesterday the German network. If I remember well, they are 10 or 12 nodes, which is not too much. The total number of the links was 23. I said 46 because each one is to be counted twice, of course, but they are symmetrical. So what you need is to make 23 evaluations of the degradation. You store this evaluation made at the beginning in a database, and when you are asked to perform rerouting because one link fails, you investigate if the rerouting, which is possible in that moment, will comply with the maximum degradation allowed. This is pre-programmed planning. The evolutionary step is to have this calculation made automatically by the management system. When the management system gets the information that a fault has been occurred, it will evaluate the new path, and it will evaluate real time if the new path is compatible with the maximum degradation. Further step, the evaluation will be made automatically by means of actual measurements, not by means of the stored value for the components. We have a database and we say, this device has an optical signal-to-noise ratio of 20, and we put it in the database. But if this, during the life, is degraded, it will not more be 20 dB. It will be 25. So the last step is to measure the optical signal-to-noise ratio here, is to measure here, and to compute by measurement what is the real degradation. This is the last evolution of the network. After this last evolution, the only improvement I can see today, from my experience of person that has been working 35 years on optical fiber system, is the introduction of optical 3R regenerators. There is nothing more to do. I hope this answered your question. You have to store the degradation for each link. And afterwards, you have only to add the degradation of the various links. So if you are going directly from A to B with a degradation, let's say 20, and you have to restore the path because this link is broken, you will go from A to Z to B, but from A to Z is still 20. From Z to B is 21, and you have to wonder if 20 plus 21 is still an acceptable value. But you have all the values already stored, so you have, it's only a matter of addition. This was last slide. Chapter 8 is finished, so that if there are any questions, as you can see, it is a chapter devoted to WDM, so also the thanks are covered. Any question? So it's just noon, and we can reconvene after lunch at 2 o'clock. In the afternoon, and maybe the first part of the morning tomorrow, we shall finish chapter 9. For chapter 10, I have very few slides because I take out only the reliability and maintenance aspects related to optical fiber system, not those for fibers or related to fire and so on. So I think that definitely we will finish tomorrow by 2:30. The afternoon will be free.
Okay, thank you, Giancarlo. Go directly to standardization sector, which is ITT. And click there, and you will see welcome on this sector. Okay, so when you see here, you can go to ITT recommendation here, and you see it here, and then you will have some details on all the ITT recommendation, going from all the man-made operating system and so on. So in this page, you have some information. Of course, you can have it in French for those who are interested in French language. It's open in the 6 official languages of the Union. And you will see all the series of recommendations and the purpose of those recommendations from A to Z. And of course, as you are now aware, for optical transmission network is on the G series. So you come here at G, transmission system, media, digital system and networks, and you click here, and you will have all the G recommendations. There's so many G recommendations, more than 3,000, and you have to go in the series G90 and X. So 900, 1290, and you will see. If you are here, take the time to download this because you have so many recommendations. Here they are. So you all know that, okay, you see here, so we have these three adolescent system to navigate inside, and you go directly on the G here, you see G400 is a characteristic of all the international carrier ports and so on. This is related to, and you will have here at G900, you see here digital, and you will see here access, or what is this here? Access optical line system from the G970 to optical submarine cables, which was what we are discussing about. Maybe if you need to see some of these recommendations, you click here, you have the details of the G970 to 980, and you will have them here listed, and maybe I can take characteristic of optical fiber submarine cables, G978, so it is here. Click on this one if you need to see this one, for example. If it works, yes, it should. So you see the FEC are here for one error correction for submarine cables. If you need some more details on the FEC, you can go there and see the updates. So here you have the update file. The G90 has been reviewed in this year in July, and so you have the latest recommendation updated by it. So you see here, I can push it a bit here, yes, and you can download it here. You see, you download here, it's in force now because you have the approval mechanism of IT3 and to approve even by correspondence or directly in the approval, fast approval way, the recommendation, and you can download them here. And so you click download, for example, and you have even the historical approval of this recommendation. And you will find this not here, you see.
This is the publisher, so you can download for
Yes, yes. So here you see this one here, the statute, it's published, and you have a price for those who want to purchase it, who are not eligible to download it freely. And the available language for the moment is only English. As it has been approved in July, the time to make the translation of the convention, we need 6 months, because we have to translate it in the 6 official languages of IT. Russian, Spanish, French, Chinese, and so on. So when you come here, you see here what I was speaking about, TIES users. So some of them, and you need the TIES user account, but for the PDF format, theoretically you could download it freely. But if you want the world one, you need the TIES account because you have only the IQ sector numbers 1 is allowed to have a word version to propose some modification. But the PDF should be free. Some of them are free, some others are not. You have to wait the process to be there. So I'm not sure this one. I've got some of them, but this one I'm not sure you can see. If you can download it freely.
Okay. I think we can start our afternoon session dealing with the last but one chapter, chapter 9, which is devoted to optical access network, or in general, optical systems in the access network. You are aware of the fact that the access network is maybe the most important part in the network, since is where there is the maximum extension of cables, fibers, and so on, because you have to reach any customer at home. So it is the part of the network which requires most of the investment in terms of both money and design and time to set up the network. Because it is very simple to say, for example, we will bring a fiber, an optical fiber, to any building in the country. But when you have a deeper look inside the design of the network, you will see that some years are needed to perform all the works and all the installations to reach any building in the country. Well, it is called passive because there is, in general, 90% of the cases, but in some cases you must add on purpose, there is nothing which is active in the field. I mean, you don't need electricity in the field. You simply put the fiber plant and you reach the destination. So passive simply means you don't have any active components in the fiber plant. Anything who is active is either in the central office or in the customer premises or near the customer premises. This is the outline of the talk. We will have, after a short introduction, the architecture of the local access network, the architecture of optical distribution network, physical configuration of the optical distribution network, passive optical components which are needed, GPON, which means gigabit-enabled passive optical network, rich extension, which is the only case in which we put something active in the network, but to reach 80 kilometers from the central office, and at the end, the future trends. Well, what is a passive optical network? Passive optical network is an access network which starts from the central office and reach the customer by means of only a fiber plant and other passive devices with no feeded element installed in the plant. Passive optical networks are able to provide cost-effectively broadband services, which means nowadays triple play. That is, delivery of data, voice, which means telephony, and video services. You can use the same infrastructure for sending to the customer all the signal of these types. Data, which means internet, of course, voice, which means normal telephony or telephony over IP, and video, which means both radio frequency video, that is the normal channels of the broadcast TV sent of the fiber, or digital video by means, for example, of a video over IP. The PONs are characterized in general, because we have an example in which this is not true and does not apply, by the absence of any active component in the field. The only case in which we have an active component in the field is when we include a rich extender in case a long distance is required. Long distance means 80 kilometers. What is the main advantage of the passive optical network? The main advantage is the low cost. The infrastructure is shared by a number of customers, so that the total cost of per transmitted bit will be very low. There is a minimum number of optical transceivers, and the fiber plant plus the transceiver, all the costs are divided among n customers. If we make some new installation, which means we start from scratch to provide data connection to new areas in a city, what is called the greenfield application, the cost is quite similar to the cost of deployment of copper pair telephony. The network is characterized by the presence of a so-called passive splitter that can be installed anywhere. No power is needed, and the mean time before failure is essentially unlimited. They do not break ever. What is a passive splitter? Passive splitter is simply one fiber coming, two fiber going out. So the signal is divided and broadcast on the two different fibers. Instead of two, I can cascade many of them, and I can have 4, 8, 16, 32, up to 128. Yeah. Yes, if I take two fibers, this is one fiber, this is the other one. I put the fibers very close with an electrical arc. I fuse this zone. I simply remove this part. I have one pulse here, here, and here. Of course, the further result, I have minus 3 dB on each way, on each axis way. But it is very, very simple to realize. A passive splitter does not cost so much. Maybe I have not the exact figure, but when I bought one of them a few years ago, 32 ways passive splitter was something like 2,000 US dollars, but you have to divide it, the cost can be divided by the number of customers, that can be 500, for example. So the total cost per customer is very low. Moreover, being passive components, they simply do not break, are in the field forever. Data rates are upgradable as technology improves. Passive optical networks deployment started about 20 years ago, and the original bit rates were the first level of SDH, which means 155 megabit per second. Then we passed to the second level of SDH, SDH4. Now we have 2.5 gigabit per second, and very soon we shall have 10 gigabit per second and higher bit rate. They are already under standardization. Pre-standard recommendations have already been released by ITU. UTP is a copper pair, untwisted pair. Is the normal copper pair used to distribute telephony. This is the history of the PON deployment. In 1995, 7 major operators, including AT&T, Telecom Italia, Deutsche Telekom, and a few vendors, started a consortium whose name was FSAN, which means Full Service Access Network Initiative, to provide customers with the offering of multi-service broadband. At that time, the obvious choice was ATM, which had just started to be deployed, and passive optical networks. The two standards merged, and the full name was APON, which means ATM passive optical network. The year after, The name was changed to BPON, which stands for Broadband Passive Optical Network, to avoid the close association to ATM. In 1997, the technical proposal was proposed in ITU subgroup 15, and it became a standard, recommendation G.983, in 1998. 3 years later, works were started to extend the broadband passive optical networks to bit rates above 1 gigabit per second. The next step was the approbation and development of all the algorithm and operation mode of the gigabit ether, the gigabit PON, and the gigabit-enabled passive optical network became a standard under the name G.984 in the year 2003. Terminology. Like any technology, the passive optical network has its own terminology, so we will have a look inside the deployment diagram. We start from the central office. This is the central office side. We have the interface of the metro access network through a network interface. And the central office, we have just one active equipment, which is the optical line terminal, OLT, which is able to serve a lot of customers. From the OLT, we have a single fiber, which is leaving the central office and is splitted somewhere and reach the network, the optical network termination, which is called optical network unit, or ONU. The optical network unit is connected by means of a transport medium, which can be, for example, a copper pair, to the terminal equipment in the customer premises. This part of the network, I mean the passive part, including fibers and splitters, is called Optical Distribution Network, ODN. All the network is called Optical Access Network. Regarding the direction, this is a bidirectional network, of course. It is not only distribution, it's not only broadcast, but we have some return signal. We have downstream from central office to the customer, and upstream from the customer to the central office. This is the terminology you should be familiar with. This is a more clear, I think, example of the structure, of the general structure of the passive optical network. You could see an optical line transmitter in the central office, the optical distribution network, which is given by the fibers in pale green, the optical networking unit that can be in the customer home, but not necessarily there, as we shall see very soon, and the the combination of different wavelengths to transmit different signal in the two directions. From in the direction upstream, which means from the customer to the central office, we always use 1.3 micron window to transmit data. Why this choice? Well, 1.3 micron components are less expensive. So if I have to put a laser diode in the customer house, it's better to use a laser diode which costs less. And moreover, the link is concerning the data bit rate is asymmetrical, which means that the downstream flow will be at a bit rate normally higher than the upstream bit rate. There is normally a factor 4, so that if you go downstream at 622, we come upstream with 155 megabit per second. Because, of course, as in the normal internet, the data which are sent from the server to you are much more than the data you transmit to the server. Normally you say, please give me this website, and then the website arrives, but it's a lot of information. We are in this situation. So we are using the second window, 1.3 microns, to have that data transmission from the single ONU to the OLT. Data in the downstream transmission are sent at 1.49 microns. If there is a broadcast, that means a video signal which is sent to everybody, one more wavelength is present at 1.55. If broadcasting is not present, it can be used, this wavelength, 1.55, to transmit data instead of using 1.49. What is broadcast? Broadcast is the possibility to send the same signal to every customer. What does it mean in the reality? It means the fact that I have a bunch of optical TV channels which are sent to the customer, which is able to connect the TV set directly to the ONU instead of connecting it to the antenna on the roof. The signal is exactly the same, but it reaches the TV set by means of the passive optical networks and not by means of the antenna on the roof of the house. If we take a look of the services that are possible over a passive optical network, we see that, of course, the used wavelength are still the same of the previous slide. And the triple play means simply that I can send to the customer data, radio frequency video service, which means signals that can be connected directly to the TV receiver, or I can send video signal by means of IP. I can send video over IP, so that I transmit video packet over the network. What is the advantage of radio frequency video? The major advantage is that it is exactly the same system used for CATV, which is a community antenna television, so that it can replace the costly coaxial cable plant in those countries in which CATV is. You have to note that a passive splitter is reported in the picture, and between brackets you see up to 1 to 64, which means that you can have just one fiber going out of the optical line transmitter, and somewhere in the field you can have a splitting up to 64 fibers. Of course, it is not needed to have just one splitter. You can reach exactly the same result by putting several splitters in cascade. It means, for example, that there you can have a passive splitter 1 to 4, and afterwards on each of the 4 fibers going out from the splitter, you can have another splitter 1 to 16. The important is that at the end you get 1 to 64.
The passive split up to 164. Is it the maximum, or we have a new, like 128?
Well, it is the maximum we have in the recommendation, but we have an extension to 1 to 128. What's the problem? Because we have to limit the number of passive branches. It's very simple. As I have shown you in this very simple example, if I divide the power into branches, on each branch I have a loss of 3 dB. It is a theoretical loss. To this loss I have to add the insertion loss of the splitter, which is due to the fact that the splitter is not a perfect component. When you do it, when you make it, you make some mistake and the attenuation will increase. Well, if we consider 1 to 64, 64 is 2 to the 6, to the power 6. It means that from a theoretical point of view, on each exit fiber, you will have a loss of 18 dBs. You have to make your multiplication 3 times 6, which is the exponent, 2 to the 6. To the 18 dBs, you have to add the insertion loss of the splitter, being it not perfect, which can account for other 2 dBs. So that here, 0 dBm, here you have minus 20 dBm. And since passive optical networks are deployed up to 20 kilometers, you have to add at least other 8 dB for the fiber loss, which is 28 dB of total loss, which starts to be too much. If you go to the next step, which is 1 to 128, you will add other 3 dB to the loss. But we shall see them in details in the table I'm going to present you and that were extracted from the relevant recommendations. What about the bandwidth to be used? It was decided to use the same bandwidth for both directions, and as I told you at the beginning, the second window bandwidth was used mainly because of ease of realization of components. Components working in the second window are less expensive in general than components working in the third window. So since you have just one optical line terminal and a lot of optical network units, which means a lot of users, it's better to put the laser, which costs less, on the side where you have a lot of laser, which means ONU. In the optical line terminal, you can also put a costly 155 micron laser, but it's just one optical line terminal, one laser. This is the reason for allocating the second window to upstream, the third window to downstream. Afterwards, since the passive optical networks can be reused, this is a point of strength of the technology. I have a fiber plant, and on this fiber plant, I transmit data to the customer, and I get data from the customer. But since the fiber is there and it has a huge bandwidth, you can transmit all the telephone traffic of the world over just one fiber. You can reuse the fiber to transmit other information. So that the decision was taken to have other bandwidth available on the fibers, which means that since at that time the ITUT were deciding to set up the grid, the reference grid for coarse WDM transmission with 20 nanometers band between the channels, and since the coarse WDM standardization would have meant that suitable laser were going to be developed for such a technology, the same bandwidth was chosen for passive optical networks in order to save money. So that for the downstream bandwidth, some other bandwidth was taken in the second window, leaving a guard bandwidth between the various wavelengths used. Now, the situation is the one reported in this slide. And as you can see, we have this bandwidth for the upstream, the bandwidth for the data downstream, and the video can be allocated either here or here, depending on the fact that it is radio frequency video according to those recommendations, or digital video, which means video over IP. General structure of a passive optical network according to the relevant recommendation. So this is the original picture from ITUT. Of course, it has exactly the same meaning of the previous slide you saw. We start from the very left with the optical line terminal, which is located inside the central office. We go into the outside fiber plant, the ODN, optical distribution network, incorporating one splitter or more than one splitter in cascade, and then we arrive to the optical network unit. The optical network unit can be placed anywhere between the central office and the customer. The two examples here are an optical network unit located in the building, or an optical network unit located in the street, either in the cabinet or in the curb. Here we have the home of the customers, and the last drop from the optical network unit to the home is normally obtained by means of copper pairs, existing copper pairs. Because we are normally in a city environment and we have customers that already have their own distribution telephony network, you can reuse the last drop, the copper pair going inside the house, because this is the most costly part of the network to replace. The copper pair reaches the network terminator inside the house of the customer. If you have in the same place optical network unit plus network terminator, the name changes to optical network termination, but it's simply the two blocks together. So if you put the ONU very close to the network terminator, you shall have just one unit, which is called optical network terminator. This is the most important slide to fully understand the topology of the network. Please, if there are questions, ask them now.
What is the difference between optical network unit and the optical network termination in terms of functionality?
The optical network termination is the optical network unit plus the network termination, where the network termination is a service adapter. It simply means that on the house side, you have the different plug to connect the Ethernet, to connect the telephone, to connect the TV. So they are two different boxes that can be combined in a single box, which is the ONT. But the functionality is exactly the same. You have the ONU. You exit with a copper pair. You enter in the network termination. If you remove the copper pair and you shrink the two boxes, you will have an optical network terminator. Moreover, however, you have to consider that In this case, when you have an optical network terminator, you have just one customer, which is, for example, an enterprise, a bank, an office. In this case, only one copper pair is listed, but you have many, and each ONU is able to serve different customers. But from the point of view of the functionality, there is no difference. Of course, it depends on the bandwidth, because suppose you have 64 ONU, and suppose you are going downstream with 2.5 gigabit per second. You can have, for example, 500 customers, and you have to divide 2,500 by 500, which means 5 megabit per second per customer. So you can have a lot of customers. It depends on the bandwidth you want to give to each customer. Originally, a passive optical network was intended to serve a few hundreds of home customers, giving them a bandwidth which is comparable to the normal ADSL.
Just back on his question, for ONU and ONT. For example, if I have a state and I want to connect them, instead of to bring a fiber to each house, like 100 houses, I should bring ONU because the capacity, in terms of capacity, is high, and then I should add ADSL-B, for example, and then there should run a cable, a copper cable, for example. The copper should support up to 25.
Yeah. I would like to ask a question about the ODN. In the ODN structure, how many one fiber can be splitted? Is there any recommendation or any standard about how many times you can split a fiber?
You mean how many stages of
Cascaded,
splitting?
like
Yeah.
you've seen there, you have one fiber entering in one splitter, then you have many fibers.
Yes, the question is quite clear. Well, the recommendation is on the total number of ending fibers, which means I will have, in general, as a maximum, 1 to 64. You are asking in how many stages I can do it. Well, you have to consider the advantages. The main advantage is that if I use several stages, I can save fibers. I can save the number of installed fiber. I mean, very simple example. This is a splitter, 1 by 4. And this is a splitter, 1 by 2, 1 by 2. This length plus this, plus this, plus this, plus this is more than this. If you reach, of course, the same houses. Well, so the reason for using cascade splitting is to have less fiber in the field. You save on the cost of the fiber, the installation, everything. However, you must recall the fact that the attenuation here is given by, this is 4 times, which is 6 dB of theoretical attenuation plus the insertion loss, which could be, for example, 1 dB for a splitter of this size. If you go here, the loss here is 2 times 2 times 6 dB plus 2 times insertion loss, because you have 2 splitters, and this could be 2 dB. So also the price is not linear. If this costs, for example, $100, this tree will cost $150. So in general, there is not a recommendation, but there is a way of use that can save you money. In general, I never saw more than 2 splitting levels. In the plant, I never saw more than 2. You can have 4, but it is not very cheap. It is not economic. And usually the reach is between 10 and 20 kilometers. This is the maximum reach you can get according to the standards, because otherwise the loss will be too high. This is what we call the physical reach, which means the maximum distance in the plant. Besides the physical reach, we have another parameter, which is the logical reach. The logical reach simply means the maximum distance that the system can cover due to the protocols. Let's say the optical line terminal send a message to the ONU and wait for a return message. The maximum delay that can be tolerated, otherwise the OLT will decide that the ONU did not receive the message, is corresponding to 120 kilometers, which is 60 kilometers going downstream and 60 going upstream, plus the delay needed for the ONU to respond properly. So the logical reach is the maximum distance that could be accommodated by the used protocols if the physical parameter were good enough. If you, in 10 years, in 10 years, will get fiber with no attenuation, will get a splitter with no attenuation, it is impossible, of course, both conditions are possible, but, or if you are able to send into the fiber 1 watt of power, you could go beyond the 20 kilometers, but up to 60, which is the logical, maximum logical reach. Above 60, you need another protocol, which means another system. We have already said everything from this slide, except the last bullet. The last bullet says the PON splitters can be placed near the OLT or at the user site, which means that I can have just one fiber going from the OLT to a complex of building and put the splitter just in the middle of the various buildings and to serve all the buildings. But the other way around is that I can put the splitter in the central office This is the central office. Here I have the OLT, and I have the splitter immediately near the OLT. And I exit directly with 32 fibers. It seems to be a useless situation because you don't save any money on the fiber plant because you are going from the central office to the houses with one fiber, but nevertheless it has been used during the first installation. The first installation in the world were realized according to this scheme, with a splitter inside the central office, which allowed to control everything in the same place.